And I know you've defined osmosis many times in your various scientific classes, but let's just do it again real quick. Because the reason this is important is because it's going to influence the distribution of water. So the distribution of fluids is influenced by the osmotic movement of water. All right? Water diffuses from a region of higher water concentration to a region of lower. The greater the solute concentration, the lower the water concentration. So the more solute I have, the less the water concentration. And water is passive diffusion. Osmosis is passive diffusion. You must be able to work with the concept of osmotic gradients for step one. All right, let's think about osmotic gradients and osmotic properties. We can define the osmotic properties of a solution as either osmolarity or osmolality. Doesn't matter clinically. Does not matter clinically. All this is a quantitation of the osmotic properties of a solution. Osmolarity is concentration of particles per liter of solution. Osmolality is concentration of particles per kilogram of solvent. Water is the main one here. So from a clinical perspective, we consider these the same. Osmolality, osmolarity. All it is doing is defining the osmotic properties. So the term I'm going to use, the ones I use with my student, is osmolality. If you're accustomed to osmolarity, just in your brain switch. When I say osmolarity, then just think osmolarity. If I say osmolality, you think osmolarity, it's good enough. It's good enough. Okay? So don't get hung up on the subtleties of the difference. As if you were in a chemistry lab, ooh, they wouldn't like you. They wouldn't like, yeah. If you're a research scientist in a chemistry lab, ooh, you'd have to know, ooh, you better know the difference. But we're not doing that. We're taking step one. So it's all good. It's all good. We don't have to worry about it. Don't have to worry about it. Again, I'm going to tend to use the word osmolality because that's what I use with my students. All right. Again, osmolality, osmolarity is the concentration of the particles. So osmolality is telling you about the osmotic properties. In your book, you have this little picture, but I'm going to change it a little bit. I'm going to very simple diagram. I'm going to make it a cell. Here's a physiologist's rendition of a cell. We try to make things very, very simple. Let's start with simple and then build up. Let's make that core, make that core solid, okay? And we can do that if we start very simple. So what I'm going to do is I'm going to say, here's a cell, okay? I'm going to put a bunch of solute around it. So the little round dots represent solute. All right. Does everybody see that I have more solute outside than I have inside? Is everybody good with that? Got more solute outside than inside. So just like in your book, panel A, panel B, and panel A. But I'm just going to do it from a cell standpoint because, you know, we don't think of things in a beaker. We're thinking of things in the body. This is step one. We want to know what's happening in the body. All right, I have more solute out than in. And just for the sake of discussion, I'm going to make my solute glucose. Okay? I could pick any solute. I'm just going to pick glucose. I'm going to pick glucose. And I'm going to say glucose can't get across the cell. Can't get into the cell. So my solute can't cross the cell membrane. All right, let's put some numbers in to work with it. Let's just say that it's 100 milliosmol per kilo glucose inside and 200 milliosmol outside. Is everybody okay with that? Right? Because I have twice as many blue on the outside as I have on the inside. So I'll just make the concentration twice. Okay? Okay? Make sense? Now, if glucose can't cross, which way is water going to go? What's going to happen to that cell? What's going to happen to that cell? Water's going to move out of the cell, which will make it shrink. So I'll get a net transfer of water from inside to outside. Why? Because the water concentration is less outside because I have more solute. Must be able to work with the idea of osmotic gradients. So there's you an osmotic gradient, and water leaves the cell. Now, this is only true if glucose can't cross the membrane, semi-permeable membrane. So I made it so glucose can't cross. If glucose could cross, then it would, wouldn't it? Do you agree glucose would move from out to in if it could cross? It moved from out to in if it could cross. And if it could cross and it goes from out to in, there would be no osmotic gradient, so water wouldn't move. But I made the scenario that glucose can't cross the membrane. Therefore, glucose is what we call an effective osmole for the extracellular compartment. Okay, that is in your book. So we'll just stop there and make sure you can absorb that idea. In case you've never heard the term effective osmole, because I use it a lot. And it's a good term because it makes good sense. Makes good sense. I'll state it again. In this scenario, my solute can't cross the membrane, so glucose can't cross. Because it can't cross, it can cause water to move. So it's an effective osmole for outside the cell. In other words, the extracellular compartment. That's what an effective osmole means. That's what an effective osmole means. Okay? So what's our, under normal circumstances, what was that electrolyte that doesn't easily cross the cell membrane? What was that electrolyte that didn't cross the cell membrane easily? Sodium. So sodium is an effective osmole for the extracellular space. Do you see the terminology? Sodium is an effective osmole for the extracellular space. Albumin is an effective osmole for the vascular compartment, so the plasma. It's a great term. Gets us right to the point very, very quick. Now, I chose glucose, which some of you are probably sitting there going, well, that's an odd choice, because glucose normally gets in the cell. Why did you pick glucose? Well, I mean, glucose normally gets in the cell, and what's that dependent transporter in skeletal muscle and adipose tissue? What GLUT transporter is that? Does anybody remember? Carolina. Ah, GLUT4. Good. Yeah. And what is it dependent upon? What compound is it dependent upon? GLUT4 transporters? Insulin. Exactly. So, but if glucose normally gets in the cell, but do we ever have a pathologic condition where glucose doesn't easily get into the cell? Does that ever exist pathologically? Exactly. Diabetes mellitus. Bingo. So here's the key element. We have to understand our core principles of osmotic gradients. We understand glucose gets into the cell, GLUT4, adipose, skeletal muscle. So it's not that effective of an osmole in the extracellular space. But we also have to be able to work with the idea in pathology states. In diabetes mellitus, glucose is building up outside the cell. That pulls water from the inside compartment, where there's more, to the extracellular compartment. Key thing to know and appreciate in somebody who has uncontrolled diabetes. What happens? Their cells are shrinking, so they get dry mucous membranes, they get thirsty. Hey, makes sense, doesn't it? Dehydrated, exactly. And part of the reason they get dehydrated is because of the osmotic movement of water, because glucose can't get into the cell. That's not the only reason. The kidneys start dumping out a lot of fluid as well. We'll talk to that We'll talk about that when we get to the kidney. But that's a key element. So understanding our core allows us to apply the principles under a variety of conditions. We're not memorizing all these conditions. We just say, hey, I know in diabetes mellitus, glucose can't cross the cell membrane. So, hey, it's going to pull water. It's going to pull water. It's an effective osmole. Okay? So, very important construct. Must be able to work with the idea of osmotic gradients.